Hello everyone, I am Sharani. Welcome back to my channel. Today in this video, I am going to explain about the real numbers in the first exercise. In the first question, use Euclid's algorithm to find the HCF of 900 and 270. That is the first sum. Now here, just first one solution, 900 and 270 is given. Let A equal to 900 and B equal to 270. Just you have to consider like this. Always big number you have to assume as A and second number small number B. Now what is Euclid's division algorithm? By Euclid's division algorithm, according to that Euclid's division algorithm, A equal, what is Euclid's division algorithm? A equal to BQ plus R, where A and B are integers and Q is the quotient and R is the remainder. Now these two numbers you have to write in the form of A equal to BQ plus R, where A equal how much? 900. 900 equal to, that means A equal, here I am writing A equal to BQ plus R. Now here, where A is 900, 900 equal to, where B is 270, multiplication of quotient value. That means 270 divides 900, how many times? Just you have to write down. This is nearly 3. So, 3 3 is 9. That means this is less than 300. So, it goes in 900 3 times. So, 3 times means 270 into 3. That means 0, you can leave it. Now, multiply 7 3 is 21, 3 2 is 6, 6 plus 2, 8. That means 8, 10 is the multiplication value. So, here how many times? 3 times plus remainder equal to how much? 900 minus 810 equal to 90. Like that. In mind also you can calculate. If it is difficult to multiply, then you have to multiply here. So 270 goes in 900 or 270 divides 900 3 times. The remainder equal to 90. Now here. Now again this big number you have to consider as A. That equal to 270 equal to small number consider as B. B, that means 90 divides 270, how many times? Leave about the 0. Just leave it. 9th table just you have to read. 9 3 is 27. That means 3 times it divides 270. So 90 into 3 exactly divides. So the remainder equal to 0. So till getting of remainder value 0, you have to follow like this. This is the procedure. Now what is the HCF value? Whatever the last divisor is there, that is nothing but the HCF of the given values. Therefore, HCF of 900 and 270 is 90 is the answer. This is the answer. Now second one. What is the second one solution? Just here see. 196 and 38,220. These two are the given numbers. Now here assume as, let A equal to 38,220 and B equal to 196. By Euclid's division algorithm, that is in the form of A equal to, what is Euclid division algorithm? A equal to BQ plus R, where A equal how much? 38,220 equal to, where B equal to 196. So 196 into quotient value have to write down. So 196 goes in 38,220. How many times? You have to check it. So this is a very big number. We don't know 196th table. So what you have to do? Just round off number you have to consider. 196 is the nearest to which round off number? 200. That means second table you can consider. So 2 goes in 38,220. That means how many times? 2 after 2 zeros, after that you can include. In this 382, that means 2 goes in 1 2 ja, again 1 200 200. So otherwise 1 2 ja, again here 9 2 ja, again 1 1 0. By 2 if you do, then you will get like this. So, but how many times divides 200? No, so what you have to do? Simply you have to assume 196 is nearest to 200. So 200 goes in this one time. That is, in this one time is 382 minus 200 is 182. Again 182. In 182 it is not divisible. So next 2 also you have to consider. That means 1822. In this how many times? Just I will show here. 38,220 goes in 196. 196 is nearest to 200. I am telling you. You have to consider just nearest value can find out like this. So in this one time, again balance here 281. Next 2 take down. Again now in this 2 9 ja 18. So 1800. Again subtract 22. Again 0 you are getting. So how many times? So remainder 20 you are getting. That means more than 190 you will get. So 191 times, that is if the 200, if the B value is 200, then 191 times it divides this number. So now what we have to do? More than 190 only it is possible. So how can you check it? Otherwise one simple trick I will tell you here. 38,220 divided by 196. Just ratio you have to consider in this. This is nearest to 200, that already I told. 200 here, 200 how many times 2 is divisible like this? 1 200 ja, in this 1 200 and 9 times and 191. 1 is to 191 times it is number and divides this number. So here how many times it is this number divisible by this number means just nearly that 196 multiplication of 194. Just I am checking here. 6 4 ja 24, 9 4 ja 36, 36 plus 2 38, 4 1 ja 4, 4 plus 3 7. Again 1 6 ja 1 9 ja 1. Again 4 14 17 2. That is, sorry, one more number you have to do. Again 1 6 ja 196 multiplication of 195. I am checking. 6 5 ja 33. Again here 9 5 ja 45. 45 plus 3 48. 5 5 plus 4 9. 9 6 ja 54. 9 9 ja 81. 81 plus 5 86. 9 1 ja 9. 9 plus 8 17. Again 1 6 ja 1 9 ja 1 1 ja. Now 0, 12, 7, 7 plus 6, 13, 13 plus 9, 22, 11, 11 plus 7, 18, that is 3. 3 ones 3. So how many times this number divides this number? 195 times. And the rough only you have to check it once. Nearest value, how many times this number divide this number, just you have to assume like that. Round off number you have to consider, like that you can assume that. So after that, next numbers you have to check it, then you will get the perfect number, exact number you can find out. Now here 195 is 196 is exactly 38,220. So remainder equal to 0. Whenever you are getting 0 here, this last divisor is nothing but the HCF of the given value. So many the students, they are confusing here 196 and 195. Why? Because both are nearest one value, one number only difference. 6 and 5, nearest values. So which is the right answer? They are confusing. You have to remember that which number is the last divisor or which is the last divisor, that is only the HCF of the given numbers. Therefore, HCF of 38,220 and 196 is 196 is the answer. This is only the answer. Next bit is 1651 and 2032. Here again you have to assume as let A equal to 2032 and B equal to 1651. Now here 2032 equal to, by Euclid's division algorithm, by Euclid's division algorithm, just you have to write here 2032 equal to 2032 equal to B 1651. Multiplication of quotient value have to write. 1651 goes in 2032 how many times? One time only. Why? Because this is also 4-digit number, this is also 4-digit number. Nearest value only, so one time only it divides. Plus remainder equal how much? Now subtract 2 minus 1, 1. 3 minus 5 is not possible. Borrow 1, 13 minus 1, 8. Here 0 becomes 9. 9 minus 6, 3. And here already we have given 1. So 1 minus 1, 0. The remainder equal to 381. Now here you have to consider as 1651 as A, that equal to 381 multiplication. 3 goes in 1651 how many times? 381 nearest to 4. 4 how many times? 4 4 just 16. Just I am checking here. 381 4s. 4 1 ja 4. 32. 12 plus 3 15. Yes. How many times? 3 times. 3 times if you multiply, how much you are getting? 1524. So now subtract here. 1 minus 4. Is it possible? No. Borrow 11 minus 4. That is 7. Here 4. 4 minus 2. 2. Here already 1 we have given. Here only given. Now 6. 6 minus 5. 1. Remainder equal to 127. Now you have to consider as 381 as E equal to B is 127 multiplication of this. How many times is divisible? It divides, or this number divisible by 127 how many times? Now see. 7 3 ja. Check it here. 7 3 ja 21. 3 2 ja 6. 6 plus 2 8 and 3 1 ja 3. Exactly you got it. So 127 into 3 plus remainder value is 0. Which is the last divisor here? 127. So HCF of the given values, these two are 1651 and 2032 is, what is the HCF value? 127. This is the right answer. Therefore, HCF of 1651 and 2032 is 127. This is the answer. Is it clear? Next question. Use Euclid's division lemma to show that any positive odd integer is of the form 6u plus 1 or 6q plus 3 or 6q plus 5 when q is some integer. Now here, first in this, here use Euclid division lemma, show that any positive odd integer is of the form any positive odd integers. First you have to assume that let A be any positive odd integer. Is of the form any positive odd integer is of the form which form 6q plus 1 or 6q plus 3. That means Euclid's division algorithm. What is Euclid's division lemma or algorithm? A equal to BQ plus R, where A is any positive odd integer. BQ plus R, B in place of B, whatever the number is given, that you have to assume as B. So let A be any positive integer and B equal to 6. Then by Euclid's division lemma, A equal to BQ plus R. So here A equal to 6Q plus R. Whenever A value and B value you know, then by applying Euclid's division lemma, what it becomes? According to that Euclid's division algorithm, that A equal to 6Q plus R. First here you have to write down. Where Q is some integer, where Q is some integer, Q value is always greater than or equal to 0 and R value, remainder value is greater than or equal to 0 and less than quotient value. That means here, sorry, not quotient, divisor value, or here B value. What is divisor here? 6. Then whenever here R value, remainder value is greater than or equal to 0 or less than 6, then the possible remainders are then the possible remainders are 0, 1, 2, 3, 4 and 5. Any other number, 0 or 1 or 2 or 3, any one, 0, 1, 2, 3, any one, remainders are any of the number up to 5. That is, A can be of the form, in the form of now apply that. If A equal to here R value is 0, then A is in the form of A equal to 6Q. How it becomes? See now, if R equal to 0, possible remainders are 0 to 5. One by one if you take, if R equal to 0, then A equal to 6Q plus 0, then you are getting 6Q. What we will get? 6Q. That means, so A can be in the form of 6Q, then 6Q plus 1 or 6Q plus 2 or 6Q plus 3 or 6Q plus 4 or 6Q plus 5. Any of the value you can get. Now, but here what is the condition? A be any positive odd integer, not even integer, positive integer only. Since A can be, here A is a only positive integer, so A cannot be in the form of of 6Q. Why? Because 6Q is the even integer. How can you say 6? You can write 2 into 3. 2 multiple of 3Q. 2 multiples all are even number. So 6Q can be written as 2 into 3Q. Like that. And 6Q plus 2. 6Q plus 2 also you can write 2 if you take it as a common. Then 2 divides 6 3 times 3Q plus 1. As well as 6Q plus 4. Why? Because here this also you can say that 2 you can take it as a common, again 3Q plus 4. So since A cannot be in the form of 6Q or 6Q plus 2 or 6Q plus 4, but A can be in the form of A is, here what is given? A be any other positive integer. Positive odd integer. Then A be in the form, then A be in the form of A be in the form of 6q plus 1 plus 1. 6q is a even number. If you are adding 1, then that is the odd number. 6q plus 1 or 6q plus 3 or 6q plus 5. That is already given here. This is the solution. Do you have any doubts? Like those type of sums, first what you have to do? First you have to assume that whatever the value is given, how you have to show that. That will give you in the question clearly. You have to show that any positive odd integer is given. That you have to assume as A. Let A be any positive odd integer. And B equal to, here whatever the value is given in place of B, that value you have to consider as B. So, and B equal to 6. Whenever you know that A and B values, then apply that Euclid's division lemma or algorithm, both are same. That is A equal to BQ plus R, where B equal to 6. 6Q plus R. In this equation, where Q is a quotient and R is a remainder, and Q is also some integer, and Q value is always greater than or equal to 0, and the remainder value is always greater than or equal to 0 or less than 6. Whenever you are getting this condition, then what are the possible remainders? Then the possible remainders are 0, 1, 2, 3, 4 and 5. These are all the possible remainders. Whenever you are getting remainders, then A can be in the form of 1 by 1 you have to substitute in this equation. If R equal to 0, then 6q plus 0, 6q. If R equal to 1, 6q plus 1. If R equal to 2, 6q plus 2. Like that you will get 6q to 6q plus 5. Now, till that is same. Next, what is the procedure here? Here the condition is A can be in the, A is any positive odd integer. Only odd integer only. Not even integer. So, since A cannot be in the form of 6q, even integers. So, cannot be in the form of 6q, 6q plus 2 or 6q plus 4. Now, A can be, now A be any other positive odd integer, then A be in the form of 6q plus 1 or 6q plus 3 or 6q plus 5. Is it clear? If you have any doubt, ask me in the comment section. Next question here. Use Euclid's division lemma to show that the square of any positive integer is of the form 3p, 3p plus 1. Here you have to assume that whatever is given in the question. So, use this Euclid division lemma. What you have to show that the square of any positive integer. Let A be the square of any positive integer. And B value equal, these are the form, which form? 3p, 3p plus 1. In place of B, what are the values given, that you have to assume as B, and B equal to 3. First you have to consider A and B. Then by applying Euclid's division lemma, A equal to 3q plus R, where Q is some integer. A equal to BQ plus R, that is a Euclid's division algorithm. Here B equal to 3, you have to apply these two values. In place of A as 3 you have to write. In place of B, you have to write on 3. So A equal to 3q plus R. Now here, Q is some integer and Q value is always greater than or equal to 0 and remainder value R value is greater than or equal to 0 and less than B value. What is the value of B? 3. Whenever remainder value is less than 3, then the possible remainders are are 0, 1 and 2. Less than 3, I have to write a 0 to 2. That is, A can be, whenever remainders you know, that means 0, 1 and 2, then A can be in the form of, what are the form? In the form of, just apply the remainder values. Here R equal to, if R equal to 0, in the form of 1 I am showing here. If R equal to 0, then A equal to BQ plus or where BQ 3Q plus R means R value is 0. Then you are getting A equal to 3Q. That equal to 3Q. A can be in the form of 3Q or like this. If R equal to 1, then A equal to 3Q plus 1. Like this. If R equal to 2, then A equal to 3Q plus 1. We know that till this is same. But here what is the condition? Use Euclid division algorithm to show that square of any positive integer is of the form. Let A be in the form of, let A be the any positive integer is of the form integer is of the form of 3Q. But here A square of any positive integer, A equal to 3Q if you know, then A square equal to, that means square of the integer equal to A square equal to 3Q whole square. Now 3Q whole square equal how much? 3 3 is 9. 9Q square. This can be written as 3 divides 9 3 times, 3 into 3Q square. Where 3Q square you can take it as here which letter is given? P. You have to show in the form of any square of the positive integer is in the form of 3P. So where 3Q square equal to P here, since 3Q square or take, just you can write 3Q square equal to P. Then 3Q square equal to P means this is in the form of P, where A square equal to 3 square of any positive integer. Now we got it here in terms of 3P. Like this. If A equal to, next one, what we got? 3Q or 3Q plus 1. So 3Q plus 1 whole square. A square equal to 3Q plus 1 whole square. Now this is in the form of A plus B whole square, that equal to A square plus B square plus 2AB, where A square is 3Q whole square plus 2AB plus B square. Any other order you can write. 2AB, 2 into 2 3 is 6Q plus 1. Again this can be written as 3Q square is nothing but 9Q square plus 6Q plus 1. In both the terms 3 you can take it as a common. So 3 into 3Q square plus 3 divides 6 2 times. So here 3 2Q plus 1. Now here take 3Q square plus 2Q equal to P. Why? Because in the question is given you have to show that any of the positive, any square of the positive integer is the form of 3P and 3P plus 1. So due to that I am taking only 3 is a common here. Remaining extra terms all I have written in the bracket and a plus 1. Now take 3Q square plus 2Q equal to P. Now here 3p plus 1. So we got it here 3p plus 1. This value equal to, we got it here 3p plus 1. So the square of any positive integer is the form of 3p and 3p plus 1. That is the answer. There. Here last you have to write down, therefore the square of any positive integer is of the form of 3p or 3p plus 1. That is the answer. Any doubts? Is it clear? It's very very important. So please concentrate. Next question here. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Now here same. Let A be the cube of any positive integer. What you have to show here? Show that the Euclid's, use that Euclid's division lemma to show that the cube of any positive integer is of the form. So A you have to assume as that the cube of any positive integer and B value equal to how much? In place of B, whatever the value is given, that you have to consider as B, where B equal to 9. Whenever you know that A and B values, now apply that. Then by applying Euclid's division lemma, Euclid's division lemma, what it becomes? A equal to BQ plus R, that is the Euclid's division algorithm or division lemma. So A equal to B, where B equal how much? 9Q plus R. Now in the first you have to apply to that A and B values to that Euclid's division algorithm. Then you are getting A equal to 9Q plus R in this. Now here Q is some integer and Q value is always greater than or equal to 0. Integer and Q is greater than or equal to 0 and R is remainder value. Remainder value is always greater than or equal to 0 and less than Q value, less than B value. What is the B? 9, less than B. Then the possible remainders are are 0, 1, 2, 3 and so on up to 8. Less than 9. So 0 to 8 are the possible remainder. That is, A can be of the form, A can be in the form of here 9Q plus R, where R equal to 0, then you will get 9Q comma 9Q plus 1. If R equal to 1, then it will become 9Q plus 1. Like that 9Q plus 2 and so on 9Q plus 8 till 9Q plus 8. If R equal to 8, then it will become 9Q plus 8. Now here let A be any of the, let A be the cube of any positive integer. The cube of any positive integer is of the form that is AB. First you have to assume that A be the cube of any positive integer is the form 9m is given. That means here A equal to actually what we got? 9Q. If cube of any positive integer is the form 9m is given. First you have to write down, after that you can find out the cube of any positive integer. Let A be the positive integer then A with a positive integer 9 cube. Then suppose if A cube equal to then 9 cube whole cube. That equal to 9 cube whole cube means 9 cube cube. 9 cube means 9 9 ja 81, or you write 9 into 9 square. Why? Because 9 into 9 square that equal to 9 cube. 9 into 9 square as well as cube. That equal to 9 into 9 square is nothing but 81 cube. Why I have written like this means here you have to show that cube of any positive integer is of the form 9m. That means multiplication of 9 in terms of other whatever that alphabet is given, that you can assume. So here multiplication of 9 only is given. So you have to take out of that 9, you have to take it as common. That means 9 multiples only you have to write up. 9 multiplication of extra number. Now here take this value is in terms of m. That value you have to assume as m. Why? Because here you have to show that value is 9m. The cube of positive integer is in the form of 9m. So take 81 cube equal to m. Then it will become 9m. Like that, in the form of 9m plus 1 or 9m plus 8, you can show that. One more I am showing here. A cube equal to next one 9 cube plus 1. Again here, this is in the form of a plus b whole cube. That equal a cube plus b cube plus 3ab into a plus b, or a cube plus 3a square b plus 3ab square plus b cube. So a cube, that means 9 cube whole cube, a cube plus 3a square b, that means 9 cube whole square a square b is nothing but 1 into 1 is nothing but same value into 1, 3a square b plus 3ab square, 9 cube into b square means 1 square, plus b cube is 1 cube. First you have to write down this, since a plus b whole cube equal to a cube plus 3a square b plus 3ab square plus b cube. This is the formula, or a cube plus b cube plus 3ab into a plus b, anyone you can write. Now here in this 9 cube whole cube plus 3 into 9 cube whole square, 3 into 9 square as well as q square plus 3 into 9 cube plus 1. No need to multiply here. Why? Because you have to show in terms of multiplication 9 you have to consider. So here 9 you have to take it as common, and remaining 1 9 if you take, remain 9 square is the remaining value. 9 square is nothing but 81 cube plus 9, 1 9 already left out. So one more 9 is a 3 9 ja 27 q square plus 9 already is taken. So remaining is 3 cube plus 1. Again this entire value you have to consider as m. That means take 81 cube plus 27 q square plus 3 cube equal to m. So 9m plus 1, this value equal to 9m plus 1. Therefore, the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8 also. If you consider a equal to 9 cube plus 2, then a cube equal to 9 cube plus 2 whole cube. If you do like this, then you will get like this, plus 8 you will get. This is the procedure. Is it clear? If you have any doubt, ask me in the comment section. Next, last question in this exercise. See, show that one and only one out of n plus 2 or n plus 4 is divisible by 3. where n is any positive integer. That is the condition. Here 3 numbers, only one, n plus 2 or n plus 4. Among those 3 numbers, only one number only is divisible by 3, where n is the positive integer. N value is positive integer. That is a condition. That condition here you have to show that. Among these 3, only one number only it is divisible by 3, exactly divisible by 3. So here you have to show that. First you have to assume that let a be any positive integer. Here already is given where n is any positive integer, where n be any positive integer. Now here that means where n be any positive integer already is given, or a be any positive integer. Where n is completely divisible, here a also you can assume that. If n is completely divisible by 3, suppose if n equal to 3 or n equal to 6, 6 by 3 is exactly divisible by 3, then n plus 2 means 6 plus 2, 8. n plus 2 as well as 6 plus 4 are not completely divisible by 3. Yes, that is the condition. Among those 3, only one only is exactly divisible. That here you have to show that. If n is divisible, then n plus 2 and n plus 4 are not exactly divisible by 3. First condition. That is the first case. What is the second condition? If n is not completely divisible by 3. If n equal to 4, then it is not completely divisible by 3. Yes, 4 is not completely divisible by 3. Then n leaves the remainders. What are those? 1 or 2. Why? Because remainder 3 is there. Then it is exactly divisible. So less than 3 only is possible remainders. Those are 1 or 2. This is the condition. If exactly divisible, n is exactly divisible by 3, then n plus 2 and n plus 4 are not exactly divisible by 3. Yes. If n is not completely divisible by 3, then what are the possible remainders? 1 or 2. Right. Now, if n plus 1 is divisible by 3, among those 3, n plus 2 or n plus 4, 3 is given. If n plus 1 is divisible by 3, if n equal to 2, 2 plus 1 is divisible by, that means 3 by 3 is divisible by 3, then n value and n plus 2 is not divisible by 3, or neither n or n plus 2 is divisible by 3, neither nor means no, it is not divisible. N equal to 2, if n equal to 2, then n plus 1 is divisible, then n and n plus 2 is not exactly divisible by 3. Yes, this condition is satisfied. Next, note that here n plus 1 and n plus 4 leaves the same remainders when divided by 3. Yes. Here 4 and here 1. 4 is nothing but here also remainder you will get 1 only. Why? Because divisible by 3, 1 3 is 3, remainder 1 only. Here, whenever n plus 1 and n plus 4 leaves the same remainder when divided by 3. Yes, this is also exactly correct. If n plus 2 is divisible by 3, then neither n plus 4 or n are divisible by 3. That means neither nor. N plus 2 is divisible by 3. N plus 2 is divisible by 3. If n equal to 4, 4 plus 2, or if n equal to 1, 1 plus 2, 3 by 3 is divisible by 3, but 1 plus 4, it is not divisible, as well as n is also is not divisible. Yes, so this condition is proved. So hence prove this. So this is the last question. This entire exercise depends on only that Euclid's division algorithm or Euclid's division lemma. What is Euclid's division algorithm? A equal to BQ plus R. So each and every question you have to assume as A equal to BQ plus R. In this equation where A and B are given positive integers, Q is the quotient and R is the remainder. According to that, you have to solve each and every question. Okay. Thank you all. Once again, thank you. If you have any doubts, please ask me in the comment section. Is it clear? Do you have any doubts? If you have any doubts, please ask me in the comment section. Thank you all. Once again, thank you. Please watch my videos and please subscribe my channel.